as we can calculate compound interest, we're also going to look at the number e in particular, because there is a way of doing compound interest, although not in a really realistic sense, because you're not going to really find any like accounts or money order things or whatever that are going to have interest compounded continuously. But the number e is the number that if you've had any kind of Algebra 2 course previously, maybe some kind of pre-calculus course, you may have seen the number e show up in those calculations. But for us to see how that number develops, we're going to look at our compound interest formula. But we're going to let P, R, and T all equal 1. So really the only variables we have involved still are the accumulated amount A and the number of conversion periods N, or basically the number of times you're compounding your growth rate in this case. So let's see what happens when we explore this a bit. And so as N's, when we start letting N be like 1, and if we let N be 1 and plug it into the formula, we end up getting the number 2. So basically, if N's is 2, then basically you've more or less doubled your principal amount. If we let N be 2 times, or represent like basically 2 conversion periods, it ends up being 2.25. So it gets a little higher. If I let N be 4, and I'm using these N's because like semi-annually, quarterly, monthly, these are things that we tend to look at most often, when we compound interest. The number still increases, not quite as much when I went from 2 to 2.25. Here I'm going from 2.25 to 2.44. So I'm still increasing, but not increasing as much as when I went from 2 to 2.25. And if we notice that basically when we go to the next value up from A, even though we're sometimes significantly changing N, the amount that we're changing A by is not getting bigger and bigger as well. I mean, the difference between them starts getting less and less noticeable, because when I do go up to 12 for a monthly, I'm up to 2.613035. So that's not a big difference there. It's a 0.07 difference approximately. When I let N go up to 365, like if I was compounding it daily, I'm up to 2.714, so I'm up by 0.1. So not a big jump. Going from a change of 353 for N values. It's a pretty small jump comparatively. And then if I just make N bigger and bigger, 8,760, which basically means compounded hourly. That's how many hours are in a year. That's how many hours are in a year. I'm up to 2.718127. So you notice that this A is approaching a value. I mean, as I keep getting bigger and bigger, the changeover is getting smaller and smaller. And so this number that actually we approach as we keep letting N get infinitely big is how we define the number E. So E is a number much like pi is a number for us in math. Pi is 3.14159, blah, blah, blah. E is 2.718 something, 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 something. I forget what all the values are after. I think, the 2.718282 is pretty close to not changing any further than that, unless you have more decimal places to it. So, usually if you just get this 2.7182 or 2.7183, you pretty much have where it is. So that's the approximate value of E. But E is another irrational number that is found a lot when you look at biologic systems and how they grow and other things like that. So this number was found through a lot of different patterns that happen to exist.